You can buy these mini ultrasonic levitators for under £10, but what interesting physics can we learn from them? The little pieces of polystyrene float at the nodes of a stationary wave created by the two sources of ultrasound, one at the top and one at the bottom. So let's draw in what that stationary wave would look like. The distance from one node to the next is half a wavelength, so we've got a total of 1.5 wavelengths there. Using the millimetre scale on the ruler and these guidelines that I've drawn in, we can see that it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 millimetres for that 1.5 wavelengths. With some simple maths, that tells us that one wavelength is 8.67 times 10 to the minus 3 of a metre. Assuming the speed of sound is about 346 metres per second and using the wave equation, we can calculate the frequency of the ultrasound to be approximately 40,000 Hz. Let's compare this to a more direct measurement. Let's bring in a crystal microphone and connect that to a digital oscilloscope. We're getting a fairly clear signal with a few interesting spikes on it, but let's freeze it there and find out the time of this first peak, which is at minus 38.7 microseconds, and then this other peak at 37.1 microseconds. That gives us a difference in time from this peak to this peak of 75.8 microseconds, or 75.8 times 10 to the minus 6 of a second. That time corresponds to 1, 2, 3 time periods, which tells us that one time period is equal to about 25 microseconds. We can calculate the frequency using frequency is 1 divided by the time period. And if we substitute in our value for the time period, that gives us a frequency of 39,600, or to two significant figures, 40,000 again, which is nice and consistent. Well, I hope I've given you some ideas about how you might use an ultrasonic levitator to teach some physics, but if not, maybe you can just enjoy the wonder of it.